Having looked at the capacitive and resistive sensing elements, we now take a look at the inductive sensing elements. And inductors, they are basically based on the fact that around every current carrying conductor there will be a magnetic field around it. Now, if you have a coil of conductor, the magnetic fields add up to form a larger magnetic field around the coil, like this. So they add up to make a larger magnetic field around it, and also it takes some energy to build the magnetic field, and it also takes some energy to tear it down again when the current stops or when the current turns around. So inductor will oppose the change of current. So in a circuit with an alternating current source, just like the one we had in the capacitor, if I have an inductor which is symbolized like this, this will represent impedance which resists the change in current. And of course the size of the inductor matters as well. Now we have what forms the inductor is a number of turns. So the more turns I have, the larger the inductor. So L depends on the number of turns, N. Also, if I have my turns, the same amount of turns, but I make it in a shorter length, that would improve the magnetic field that builds up. In worst case, this inductor here, a very long inductor, will make a smaller magnetic field. So the length, the shorter, the better. So the length belongs below. Also, the cross-sectional area of the turns. So if I have a very narrow coil compared to a larger one with the same amount, that would also influence on the overall inductance. In fact, the larger area would help the inductance. The last thing that has an influence on the size of the inductance is if we have something that helps the magnetic field inside the coil. Let's just clean up the board a bit and draw another coil. Here's a coil. Now, okay, that builds a current would build up a magnetic field in that coil. But if I have a piece of iron and I were to push that piece of iron inside the coil, that would help actually the magnetic field. So a coil inside will indeed influence the magnetic field. Here the inductance will be lower than here. So we need to have something to represent the presence of the coil itself. So that would be the part of the equation that you find here, the mu. So we also have mu. In fact, number of coils is number of turns in inductor is squared, which shows the importance of the number of turns in the inductor. So, if we want to manipulate the inductance of a coil, we can stretch the coil, make it longer, we can make it wider, or we can increase the number of turns. But in in most cases, those three are rather fixed because the physical properties of the coil. So therefore, the easiest thing to manipulate is to manipulate the presence of a core, the mu. So this would actually be a sensor with a high inductance, low inductance. So this would be a position sensor if I were able to remove or insert the core into the coil here. Some coils are so-called solenoid and some are toroid. Let's go back to the toroid coils and solenoid coils. Toroid coils, those are circular shaped. Of course, it should be a circle all the way around here. And those are really effective because if you have a core that touches at the end, like in a circle, in a ring shape, that will create a good path for the magnetic field all the way around the inductor. A solenoid is a linear shaped inductor with the core inside it, but of course it's easier for the linear solenoid to insert and take out the core from the inductor.